Recently, scientists have observed something, a landmark discovery in astrophysics. A mysterious filament 3 million light-years long, connecting to galaxies. Why is the discovery of this condition so important? What does his discovery mean? I am an old horse. This video, let's take a look. This important astrophysical discovery. Recently, scientists utilize VELT mounted in Grand Telescope, advanced multi-cell spectral detector on MILS, directly to this elusive structure, imaged. Captured hydrogen flowing along the interstellar highway, the faint light of Ki. After calculation, in the cosmic web, a filament 3 million light-years long, connecting to galaxies. The universe was only 2 billion years old. The science and technology that made this discovery possible. It symbolizes our understanding of the universe, structure, and galaxy formation, an important milestone in understanding. From the discovery of this 3 million light-year-long thin silk began to speak. It's connected to galaxies. This discovery is a milestone in astrophysics, monument, because he provided direct evidence of the cosmic web. Scientists have long believed that galaxies are not isolated entities. It's part of a larger interconnected fabric. However, directly check these delicate filaments. It's been a huge challenge. Until now, the research team used the intellectual Grand Telescope VELT multi-cell spectral detector on the Muse, captured this elusive structure. MIS is a sophisticated instrument capable of collecting images and spectra simultaneously. Enables scientists to examine. Hydrogen has been detected over vast interstellar distances. Light of gas. After hundreds of hours of accumulation, the team finally revealed the structure of the filament. This technology is groundbreaking because light is the most abundant element in the universe. Usually outside dense regions like stars or galaxies, only emits a faint light. This finding is particularly significant because he is based on direct observation. So far, most of our understanding of the cosmic web begins simulation from the measurement. For example, how does interstellar gas absorb background light? However, with the accuracy of MI, astronomers can directly measure the emission of light, provides clarity on the structure of the cosmic high-resolution image. And this image is not just a static snapshot. It is a dynamic record, shows how gas flows through interstellar space, connect galaxies, and promote the growth of stars and supermassive black holes. This observation confirms that the gas is moving along these thin, supports the theoretical model of galaxy formation. Another challenge in observing the cosmic web is distinguishing the light between of the stars and the faintness of interstellar gas. Integral field light. The spectrometer provides a three-dimensional view to separate the different light sources. This is where researchers can put the light of filaments separated from the surrounding cosmic environment. Make it history. One of the most detailed images of cosmic filaments. This breakthrough represents a major leap forward in observational cosmology. It directly presents a cosmic filament. To understand the significance of organization at scale, opened a new window. One of the key lessons of this discovery, it's the cosmic web fueling galaxies. Filaments are like highways. The cooled gases removed from interstellar rings are delivered directly to the galaxy. This gas is the raw material for star formation. Make the cosmic web the life infra of galaxies. Without these filaments to transport the gas, galaxies will soon run out of reserves, stopping the formation of heartbeat and slow their growth. This observation provides direct evidence of the process, confirmed theoretical predictions, further validating our current cosmological framework. The research team took their images with Max Planck, the latest simulations from the Institute for Astrophysics, the predicted filament structure vs. the observed structure. This will strengthening our understanding of galaxies and understanding of the formation and evolution of the universal structure. In addition to validating this finding also shows the distribution of matter in the universe, helps explain why galaxies will form where they are, and how they have grown over billions of years. The interplay between galaxies and the cosmic web, also to galaxies, merging stellar explosions, even the behavior of supermassive black holes had an impact. By studying more filaments, astronomers can improve their understanding of these processes and uncover new insights into the evolution of the universe. By directly imaging the cosmic web, scientists can now study with greater clarity dark matter, the interaction between gas and galaxies. The gas seen in this filament flows dynamically, helps answer basic questions. How do galaxies get the fuel they need? What triggers the explosion of star formation? How do these processes affect the overall evolution of the universe? Looking to the future, the discovery of this cosmic filament is just the beginning. This breakthrough not only validates current models, but also for a new era of exploration and discovery in cosmology. The foundation. The next phase of research will focus on draw more of these elusive filaments, perfect our simulation, and understand the cosmic web broader implications of galactic evolution. Future View survey activity will expand our view of the cosmic web. New project, whether on the ground or in space, it's all planned to further study these ideas. Mills-based success. Advanced instrumentation will be higher provided. Sensitivity and resolution. The upcoming Very Large Telescope LT will play an important role in this regard. Its dense mirrors and advanced spectrometers. This will enable astronomers to explore darker structures detected and delve deeper into the cosmic past. Another focus will be on refining theoretical models. As more cosmic filaments are observed, cosmologists will be able to compare them with models. To be compared. Further testing and improvement. Our understanding of dark matter and the structure of the universe. These improvements will provide a more comprehensive approach. Show Galaxy how to grow and interact with your surroundings. In addition, this discovery also has implications for our understanding of dark matter. The cosmic web is not shaped by dark matter that emits or absorbs light, make it difficult to detect directly. Through research, the distribution of visible gases and cosmic astronomers can deduce that the existence of dark matter on large scales and behavior, helping to unravel modern physics, one of the greatest mysteries. As we continue to push the boundaries of observational astronomy, every newly discovered filament in the world will add another piece to the cosmic puzzle. This discovery is a stepping stone towards the future. We will have a complete three-dimensional picture of the cosmic web. Witness the amazing hidden structures of the universe. Thank you for watching and joining our universe journey to stay curious. See you next time. Continue to explore the wonders of the universe. Recently, Lee Elemental has challenged the Big Bang model again and questioned the reliability of the Big Bang. Is anyone curious? The Big Bang model was established 120 years ago. Why always? Some scientists want to prove that there is no Big Bang. What are they trying to prove? Obsession and the origin of the universe. What does it mean to us? In the 1920s, after discovering that our universe is expanding, Belgian cosmologist Georges Lemaître speculated that, what if the universe got bigger and cooler? He used to be smaller and hotter. All the energy is squeezed into a smaller and smaller area. The logical conclusion to this is, if you rewind the universe, from the very beginning, all the energy of the universe will exist at a point in space. This starting point will be infinitely hot and dense. However, it is this infinity that leads to ambiguity. Einstein's theory of relativity can be used to predict motion of objects under the influence of attractive forces. But when you start to add wireless into it, no equation can describe it well. The earliest moments of the universe. What's up? Or what caused the universe to start expanding? Under an infinitely hot and dense starting point, we can't know before him. What might have happened? Any evidence before that? Or signal will be burned by the hottest thing the universe has ever devoured created by the furnace. He somehow happened. That's all we can be sure of. At the very beginning of the universe, changes in temperature and density cause matter to begin to form. After 1 second, the temperature of the universe has dropped to 100 billion degrees Celsius. Although still very hot, but it's enough for matter to start forming. After 99 seconds, the universe cooled to 1 trillion degrees Celsius. Powerful forces come into play. Protons and neutrons begin to combine to form light and knife. Hydrogen and isotopes is the most common element in the universe, but hydrogen isn't the only problem. 2 protons were created very quickly. Calculated by mass, the matter in the early universe was almost 76% hydrogen. 24% is harmful. However, it is very rare that the other proton will merge with the other 2 protons. Identical digits in formation make the number of protons in these atoms 3. Calculated by mass, this is only 0.00000007% in the early universe. But that's where the mystery comes from. By examining spectral data from stars, we can evaluate the distribution of elements in the universe. What we see is roughly in line with predictions. Our sun is measured by mass. 71% is light and 27% is harmful. 2% are other heavy elements. And these ratios are competing throughout the universe. This is the hot Big Bang model, and our equation. The process is correct. Evidence, however, we got it wrong. Although the predictions are indeed low, but the predicted value is actually more. See it 3 times higher. In other words, when we study the spectra of primitive stars, I didn't see the content we should have seen. There are more mysteries around. Leaky is what we tend to do early, the same number seen in the universe. This means that in the nucleus of a Li molecule there are 3 substances and 4 neutrons. But there's another kind of isometric, called Li-Liu. 1 less neutron should be more unstable than its counterpart, less common. Only 2 of every 100,000 Li-Yuanzi rivers. Although the total amount in the universe is too low, but the ratio of Li-6 to Li-7 is too high. Li-Liu was more likely than it should have been in the early universe. There are 1,000 times more of them. So, what does this mean for the hot Big Bang model? Our most trusted theory about the origin of the universe. Do you really need to go back to the drawing board? Not necessarily to possibilities. One involves rewriting the Big Bang theory as we know it. But there is another explanation. When confronted with something like this, one of the following 2 things must be satisfied. Either our observations are wrong, either our model is wrong. It's hard to discard the hot Big Bang model entirely. There's nothing else that really explains it. Cosmic background, the presence of radiation or hydrogen as we see in the universe, the amount of harm. Those elements are almost identical to predictions of the hot Big Bang. Exactly. This seems perfect. It can't be a coincidence. That is to say, scientists are increasingly unsure about this model because he can't stand. Stephen Hawking, once the universe started from 1, he advocates of point start, but then changed his mind. In his book A Brief History of Time, so he says, the work of Roger Penrose and I is generally accepted. Nowadays, almost everyone assumes that the universe, beginning with the Big Bang. Perhaps ironically, I changed my mind, now trying to convince other physicists. In fact, the universe began without a beginning, as we shall see later. Once quantum effects are taken into account, it will disappear. These quantum effects are too complex. It cannot be discussed in this video. And that doesn't necessarily solve the problem, even if true. But he did emphasize the cosmic, physics, and a growing branch of cosmology. A full explanation of him has yet to be found. Maybe our model, one day it will be adjusted in such a way. The problem is gone. Even the broad strokes of the theory remain. Rangley's puzzle fits well with King He-Wei. The alternative is that there's something wrong with our observations, and there's probably some reason for that, due to the small content under discussion. So it's very difficult, once you look back, long time to see the exact number of interstellar rings present. Probe interstellar, the only way to create mass is by letting light go through it and look at the spectrometer. Which shapes are blocked? This can tell scientists what elements might make up a particular nebula or dust cloud, but it's getting harder. The further the goal, finally, it's completely impossible to get an exact estimate. Instead, scientists can only focus on the original spectrogram of the beginning star. These spectrograms do not necessarily represent the entire universe of time. Stars are a special case. What happens internally may change. The amount of courtesy that exists transform the gift into something else. It also increased the number of rituals, although it is difficult to guess what the process might be. if our observations can be improved, and we can better measure the whole morning. The content in the universe. Maybe the numbers will find their way back into the queue. Maybe the problem didn't exist in the first place. Ultimately, how the universe came into being. The answer is never complete until all available data is consistent with theoretical predictions. It doesn't matter. Or some other problematic element in the universe. For example, there is too much gold outside. All these numbers have to be consistent. Much remains to be said about the origin of the universe. Solution: I do think how incredible we are, able to learn and infer events that took place billions of years ago. Matter itself has been properly formed, using only our telescopes and our minds. That picture. How did it all start? The grand vision is waiting to be assembled. However, how did the universe form? It is based on a foundation of order, allowing us to unlock its principles, sort out its mysteries, and rebuild the configuration of its various parts. One day, I am confident that we will also solve the problem, while waiting for the answer to our ultimate origin. Some issues are too important, can't be without an answer. In fact, science is all about finding the original and old horse. As an astronomy enthusiast, can't wait to see this puzzle the day it was finally completed. The cosmology community has flipped the table again. Cosmic expansion, dark energy acceleration. This could all be an illusion. This is not a marketing account. It's the latest science. A paper was published in December. Claimed dark energy. It is widely regarded as the dominant force in the universe, of energy, and at the heart of our modern model of the universe. Component. It doesn't exist. This is big news in cosmology. Because if energy doesn't exist, what about our understanding of the universe? It may have to be completely changed. This paper, by Antonia Safford of the University of Canterbury in New Zealand, and its team write. They claim that the accelerated expansion we observe comes from our understanding of inflation. Oversimplification of the cosmic model. Researchers point out that the current Lambda model did not properly consider different regions of the universe. The fact that time passes at different speeds, especially in areas of attractive force, like the density of the cosmic web, star clusters, and filamentous structures. Time passes more slowly, and in the vast open area, time flies faster. This results in the speed of time is changing the cosmic landscape. In it, some parts of the universe may be better than others, billions of years old. So it's not so much a landscape. It's more of a temporal landscape. In this model, the part of the universe where time passes faster, expanding the part that is slower than the passage of time more. This effect, it can perfectly simulate our view. Accelerated expansion phenomenon and does not require any acceleration, at least according to the team. You know, according to existing theories, the universe is not just expanding, it's accelerating. All this is due to God. Secret dark energy. Unless, of course, the cosmologists get it wrong. Dark energy doesn't exist. If so we're going back to square one. Since the discovery of dark energy, people keep claiming he doesn't exist. There are various levels of absurdity. This particular proposal received more attention than usual. Part of the reason is that he's definitely not ridiculous. This proposition has a solid foundation in science. Researchers are serious scientists. But that doesn't mean that this view is correct. Indeed, first, a quick look at dark energy. The universe is expanding, and we've measured the history of this expansion. We measure. One of the most important methods of inflating history is to measure the distance to a lunar supernova. These exploding white dwarfs burst with predictable brightness. The light from these explosions travels vast distances, come to us, and two things happen during this process. One is light, dim as photons spread through the universe. This tells us how far light has traveled and how long it took. The second is that these photons are traveling, stretched by the expansion of the universe. Redness meter. This tells us how much bloat happened during their transmission. Combine this information by many supernova go back to the early days of cosmic time. So we have the history of the expansion of the universe, the results of the first large supernova surveys discovered in the late 1990s. Scientists had expected to find the expansion is slowed by attractive forces because of Einstein's general theory of relativity, an attractive force that only pulls inward. To everyone's great surprise, they found that the expansion was actually accelerating under the current version of general relativity. That doesn't make any sense. However, in general relativity, add an extra part in U. The universe constant is just provides the acceleration required to interpret observations. We are not really exactly what's causing this accelerated expansion. The most likely candidate is some kind of vacuum energy. But whatever it is, we call this dark energy. This discovery for our supernova observers won the Nobel Prize in Physics. Dark energy exists in the form of the cosmological constant. It has now become our description of the universe. The main features of the operation on the largest scale. Mathematical model, part of the lambdic model. The lambda-lambdacom model explains a range of observations, doing so well in terms of results, so that it comes to something like dark energy exists. On the other hand, we never really directly measured the acceleration of the universe. We just found out mode with dark energy. This model is better than a model without dark energy. Fit the data. But if we make up our universe, a basic assumption of the inflationary model, is it wrong? That's basically what the temporal landscape model says. To understand the different factors driving the expansion of the universe, we need to solve for the entire universe. Equations of general relativity. This is only going on for some. It's only possible with a considerable simplification. The main simplification is, suppose matter in the universe is uniform, and the distribution of isotopes, no large-scale clumps or directionality. And we can do that with a number. The density of matter describes the effects of matter, rather than having to solve for each clump of matter individually. The result is the Friedmann equation. We have analyzed it in detail before. They describe the size of the universe over time from a uniform distribution of matter driven by constant dark energy. Add the appropriate amount of these two. You can describe our universe. This is the Lambach model. Although on a large scale, this smooth approximation looks really good. But the universe is not smooth on the small scales at a distance of about 1 billion light years. This smooth substance has split into a huge cluster of galaxies and the substance division that connects them. And by this cosmic web, it's a big hole. Cosmic void. These structures will indeed, photons passing through them have an impact. For example, when a photon falls into an attractive force field, will gain some energy, lead to blocking. And when climbing out of these attractive forces, will lose some energy, cause red meteor. Therefore, one in Rainier supernova exploding deep within the Gram supercluster, maybe because come to us through expansive space and get some red meteors, but also because we have to fight the attractive force field of the supercluster to reach the Milky Way, located on the edge of Rainiac, and get more red meteors. Local attractive force field. It also affects the velocity of nearby matter. Therefore, although this supernova, mainly due to the expansion of the universe, but because his galaxy is in any attractive force in the field, he might also have some extra speed. Whether it's laughing at us or staying away from us, we must seriously consider these factors, especially when it comes to relative competition. Supernova in the universe. But if the supernova occurs hundreds of millions of light years away, then his light, the child, is on its way to us. Will pass through multiple voids and superclusters. All the blue and red meters cancel each other out. If so, then the Friedmann equation and Lambdic, the model should be able to describe the expanding universe that these photons experience. That's what most people think. The temporal landscape models suggest otherwise. As I said at the beginning of the video, time passes more slowly in areas of high attractive force. Time passes faster in low attractive force areas. This attractive force of time dilation, it's a well-known theory of general relativity and well-tested features. But the temporal landscape model proposes the difference in the speed at which time passes There's another effect as well. He should change the universe, the rate of expansion in different places. It's straightforward. The more time passes, the universe gets bigger. So if in the cosmic void, more time has passed than in high-density areas, then the void will expand even more. This differential inflation affects the photons passing through these regions. For example, as the photons pass through the faster expanding cavity, it will be stretched more than in dense areas. More red meters occur as time goes by. Matter is getting more and more clustered together. The proportion of empty space in the universe is also increasing. This means that at night, photons traveling through the universe will be spent in the void more time. So you get more of this extra red meter. In the limbic model, it's the accelerating expansion of the universe so that the photon gets an extra red meter in the later stage. But in the temporal landscape model, is an increase in the proportion of emptiness. And it is said that global acceleration is not required in the time landscape. The temporal landscape model has been around since 2007. So the reason for the recent sensation is the team has just published a review of the largest supernova survey analysis of Panzianga's results. Overall, they discovered that temporal landscape model is better than limbic model, better match supernova data. You can see from this chart, it shows the Bayes factor. It's basically a temporal landscape. What's the ratio to lambican? If we are in the blue zone, then it leans more towards the temporal landscape model. The x-axis is a red meter stage. The dot on the left uses all the supernova, including nearby. As we move to the right, we start by ruling out supernova from the nearest. Until here, we've included only the most distant supernova. It's a nice way of presenting results, because of a nearby supernova should be more affected by non-uniformity, more affected by local clumps in the universe. So lambic doesn't do very well there. It makes sense, because it assumes perfect smoothness. Further away, that mass averaged out. Time landscape and the limbic model provides similar results. Although according to this chart, time is better at all distances. So is this correct? Has dark energy been commissioned? If supernova results are the only evidence of dark energy, then this could have implications for dark energy, and limbico is bad news, because in a sense, the temporal landscape model is simpler than the limbic model. He only uses the original general theory of relativity as Einstein envisioned. No need to add a universal statement. There are indeed other tests of the lambic model. This model here, not only is the supernova result well described, it also successfully explains a variety of other observational phenomena. For example, seed emissions shocks from very early echoing sound waves, now as a faint halo, frozen on the distribution of galaxies in the sky. The size of these rings provides an independent measurement method of expansion rate. This method is immune to cosmic voids. How to make a photon red meter affect. And neutrons are advanced. Observations of oscillations also strongly suggest accelerated expansion. The lambic model. There's also the evolution of large-scale structures. As for us at lambic, simulation running under the model, perfect fit. And the universe, a fact that is very flat in geometry. And that's going to happen. 70% of the energy in the universe must be expressed in terms of energy. A temporal landscape model can also explain these phenomena, but so far, he hasn't done it yet. Another major problem with temporal landscape models is, he needs it empty and dense. Between regions, there is a considerable time difference. The avenues are large enough to make the voids larger than billions of extra years. Such a big difference is not a consensus. For example, Eisen Sego pointed out that the relative passage of time between these regions should only lead to time differences of hundreds to thousands of years. That's nowhere near enough to produce a temporal landscape, the claimed effect. The time landscape team also acknowledges some of them require further study, so dark energy hasn't disappeared. Lambda mold. The type still provides us with insight into the large-scale universe. The most consistent description. Anyway, the mystery of dark energy remains unsolved. But every new theory and discovery. Let's get one step closer to the truth. What if I told you everything we know about the universe? Ultimately, it can be traced back to the simplest in nature, but one of the deepest components. Atoms are right. It's those atoms that are extremely small. You might ask, how is that possible? Imagine that. It's the width of a human hair, hidden around 1 million carbon atoms. These atoms are unbelievably small. Even the most powerful optical microscopes, there's nothing you can do about them, because they are better. The shortest wavelength of visible light is even smaller. Don't underestimate these little atoms. They have the ability to understand a key to the universe. An atom is the smallest unit of matter, but still retain our presence in the macroscopic world. See the chemical and physical properties. And here's what's amazing. They are still quantum real. The body has discrete energy and unique interaction properties. The amazing thing is, this humble atom, the 4 fundamental forces of nature, can interact with each other. The entire framework of physics in atoms that we can't even see with the naked eye, playing a role. Atoms are like the link between our macroscopic world, a magical bridge to the quantum world. By understanding atoms, we can uncover the mystery of how the entire universe works. You may not think our understanding of the atom is actually very young. Less than 100 years ago, scientists still arguing about what atoms look like. But the concept of atoms is not young. Can he trace it back to ancient Greece? The word atom comes from the Greek atomos. It means inseparable. The early Greek philosophers imagined, if we take any substance, keep breaking into smaller parts, one day it will become indivisible. They think they come in all shapes. Indivisible tiny objects. They make up everything in the world. This simple idea, for some of the greatest scientific discoveries of the future, laid the foundation. Come to the beginning of the 19th century. British chemist John Dalton took the idea a step further. He described the atom as indivisible. Small, hard sphere. Every element has the same atoms. That's a big step forward. But the idea that atoms are inseparable, it was soon broken. Late 19th century, J.J. Thomson discovered something shocking. Atoms are not the smallest. It's made up of smaller particles. When current flows through the vacuum tube, he observed an electric current attracted by positively charged metal plates, but it is repelled by negatively charged metal plates. This shows the current flowing through the tube is made up of particles that pay for electricity. We call these particles for electronically measuring the deflection of light beams. It was also found that these electrons are lighter than the lightest atoms, about 2,000 times lighter. Thomson then brought up the pudding. Atomic model. Electrons are like ions, scattered within positively charged spheres, but it didn't last. Thomson's student Ernest Rutherford conducted an experiment. Originally, I wanted to test the idea of plum pudding. It ended up breaking him. The experiment was simple. If the atom as a whole is neutral and the electric brown is evenly distributed, then a beam of positively charged particles in a sheet should be able to pass directly through. But Rutherford discovered, although most alpha particles pass directly through, but there are also some alpha particles. There is a large angle of deflection. A tiny fraction bounced back completely. This shows that there must be more complex structures inside atoms. Rutherford discovered the nucleus with the nave. To explain the rebound phenomenon, he thought nuclei had to be small. It's only a fem, or 10 to the 15 meters wide, and most of the atomic space is actually empty. Where electrons orbit, about 100,000 times farther from the nucleus. He felt that due to the action of electromagnetic force, electrons with secondary electricity, orbitals of positively charged nuclei. But here comes the problem again. If electrons spin around the nucleus, they will endure because of the circular orbit, constant acceleration, and the accelerating charge emits electromagnetic waves. That's light. That electron, wouldn't it quickly radiate all the energy? Inward spiral, and they crash into the nucleus. In other words, atoms can't be stable. What can be done? Don't worry, French physicist Louis, in his doctoral dissertation in 1924, proposed a revolutionary idea. Electrons are not just examples. They also behave like waves. These waves can only exist in specific, discrete energy levels. Like a guitar string waves hymn, only certain ramp or standing waves are allowed. The same is true of electrons. They orbit the nucleus in a stable pattern. The waves blend perfectly into the orbit. No more, no less. These energy levels are like steps on a ladder. Electrons can jump between them, but not in between. When electrons move from a higher energy electrode to a lower level in time, will release energy in the form of a photon, a beam of light. Photon energy accurately match the energy system between energy and energy. When an electron absorbs a photon, it's like getting quantum enhancement, jump to higher energy. And the electrons in any atom, from one ability to another, timely energy jump, it is unique to each element, is determined by the number of protons in the nucleus. They're like the fingerprint of an atom, generate unique spectral lines. Scientists can use them to identify stars, elements in galaxies, and even distant planets. It's like we can read the light of the universe to decode the composition of the universe. In this case, a photon is more than just a messenger. It also carries electromagnetic force. Let charged particles interact with each other. Electromagnetism is the second strongest fundamental force in shaping the world as we know it, plays a crucial role. It not only ensures the stability of atoms, it also determines the unique properties of each element. There are approximately 90 naturally occurring elements on Earth. They combine in countless ways, formed us in the universe. See the molecules and structures, from the simplest clean atom into complex molecules in living organisms. Atoms and their electromagnetic interactions. It's like all around us, the architect of everything and beyond. But here's the catch. The protons of the atom in Hanoi are all in the main hall. They should be due to electricity. Magnetic interactions strongly repel each other. So why don't atomic nuclei divide? Don't worry, the answer will be revealed soon. In the nucleus, protons with a main hall do not repel each other, because one of the most powerful forces in the universe, strong force or strong interaction, reacts at a distance of less than a fem. Compact ground minus 15 meters to the power dominates, overrides the electromagnetic repulsion between it's 137 times stronger than the electromagnetic force inside an atomic nucleus. This particle refers to protons and neutrons as nuclei. Put it together. But the real secret goes deeper. Protons and neutrons themselves are not inseparable. They're made of quarks, smaller particles. There are 6 types or flavors of quarks, but inside protons and neutrons, you only find 2 kinds of up and down quarks. The upper quark is 2/3 positively charged brown. Down quarks have a negative charge of 1/3. But they can only combine, form an example with an integer hertz. For example, the proton is composed of 2 up quarks and 1 down quark. Space composition. DJ's main hall. Neutrons consist of an up quark and 2 down quarks. Oidi. It's neutral. It's not over yet. Quark is not only electrically brown, it also has a so-called color brown. Attention! Now, this is not literally an optical color, just a metaphor. There are 3 colors and anti-color electric brown, red, green, and blue. For the existence of particles, the color-brown combination must be neutral or colorless. Neutral brown can be produced in 2 ways. One is the red quark. Green quarks and blue-charged quarks bind together. Another is when colored and anti-colored charged quarks combine. This rule, only 2 quark complex particles called seeds are allowed. They can be made up of 3 different colors. It's 3 quarks. This is what a proton or neutron contains. Or they can be made with color, the anti-quark quarks and the anti-quark team. That's what a muon contains. If we zoom in and see the interior of a proton or neutron, there will be powerful forces. 3 quarks are constantly exchanging across. Jiaozi is a powerful carrier. They allow for the constant exchange of sex. This can be overwhelming. The powerful appeal of letters. The intensity, that's the weight of a 10-ton truck, acts on a distance of 10 to the power minus 15 meters. And if you try to pull the quark apart, the force between them will actually get stronger, like pulling a spring, and bring them back together. Actually, if you apply enough energy to separate them, Gauzy field will break, generate new quarks. Anti-quark team, this is a ring. It is these introductions, the exchange of protons and neutrons, put them together in the nucleus of an atom. This is why quarks and prides never be seen alone. They are always locked in quality. Larger particles such as neutrons and neutrons. This powerful force determines the potential stability of a substance. It is also the driving force of stars and great lighter nuclei. They combine to form heavier nuclei, release a lot of energy, the strong energy in atomic nuclei, the same energy released in a nuclear bomb. This shows the incredible amount of energy locked inside an atom. Mighty is not the only player in the quantum world. In some types of atoms, may change radioactive processes in the formation of atomic nuclei. The most famous is alpha decay. The nucleus is ejected. Alpha particles break into smaller pieces. Alpha particles are composed of two substances, two neutrons, same as the nucleus. This is caused by strong interaction and electromagnetic interaction. However, less common steel decay. That is, neutrons are converted into protons. Simultaneous emission of electrons and antineutrons can't be explained by these two forces. At first glance, the emission of electrons may resemble an electromagnetic process, but the participation of uncharged neutrons and neutrinos means that this decay is a completely new result of fundamental force. This force is called the weak force. His name is apt, because he's 1,000,000 times weaker than a fem. The weak force has an extremely short range of action, only about 0.1% of the proton diameter. This is due to his intermediary W and Z bosons. Unlike photons and Gauzy, these particles are very massive. That's about 80 times the mass of a proton. You might ask, how is it inside the proton produce something 80 times the mass of a proton? That's the magic of quantum mechanics. Massive particles may spontaneously arise. According to Heisenberg's uncertainty principle, such large energy fluctuations could exist, but only for a short time. This makes the weak force short-lived and localized. However, it's the only force that can change the properties of quarks. This means that he can turn down quarks into up quarks, convert neutrons into protons, and vice versa. Beta decay has other useful applications, such as carbon-14. He has 6 protons and 8 neutrons. Instability over time. One of the neutrons turns into a proton, into nitrogen-14. The half-life is 5,730 years. So, archaeologists can learn by looking at the carbon in fossils, the ratio of 14 to ordinary carbon to determine the age of fossils. You might ask, interactions that change the properties of elements, should it really be called profit? After all, the intuitive definition of profit is attraction, something that repels or causes an object to move, and the same is true of the weak force. Due to the conservation of momentum, launch W or Z, the Boser particles will recoil in the opposite direction. Particles that absorb such bothans, it gains momentum in the direction of its propagation. Can be imagined as, from one stationary ship to another. Throw a heavy ball. The two ships began to move away from each other, seems to feel a repulsion. Of course, in the case of the weak force, any resulting movement is within a very small range, happens almost imperceptibly. The weak force is a name that doesn't sound important, but he plays a crucial role in the universe. Inside the fresh, it generates neutrons required to initiate and coalesce into harm. Without it, stars as we know them don't shine. It also cannot synthesize the heavier elements required for life. If the word is a bit misleading, it's not actually the weakest in the universe. The gravity we constantly experience in our daily lives is much weaker than the weak force at the principal scale. In fact, it's about 1,312 times weaker than the weak force. 1,316 times weaker than the electromagnetic force. This is a Van der Graaf generator, a device for generating static electricity on a metal ball. It can overcome the gravity of the entire Earth. Raise all these ropes. You can also try a similar experiment at home, rubbing balloons on shirts. Some electrons have been deposited on it. Then bring it close to the hair. He will lift the branches of your hair. So the attractive force is really weak, but due to the overall neutrality of the atom. Attractive forces shape the universe as we know it. Pull matter together. They create massive structures. In these structures, galaxies, stars, and planets like ours can form. All atoms are determined by their mass. It interacts with gravity. Pay attention to the basic level. Elementary particles in atoms and the masses of quarks and electrons from their interaction with Higgs field. Use it, but you might be surprised to find out atomic mass only about 1% from the sum of the masses of its basic components. Where does the remaining 99% come from? According to general relativity, any object with energy have the ability to bend the fabric of space-time, and that curvature is what gives rise to gravity. The nucleus of an atom contains a tremendous amount of energy concentrated in atomic nuclei. The strong interactions between quarks. Einstein's equation is equal to mc2, which reminds us from intense energy generates the remaining mass of the atom and the attractive forces we observe. The most important point is every fundamental force can be observed inside an atom, from the strong force that holds quarks together, to the weak force conversion element, to the electromagnetic force that binds electrons to atomic nuclei, even the gravity that shapes spacetime itself. All of this, it's in the simplest building blocks of matter. This means that atoms are not only the foundation of all matter, it is also our understanding of the fundamental the largest window created. We are interested in this inconspicuous entity. The more you know, the more we can uncover the depths of the universe itself. Elegant. So if someone asks this question, how do we know so much about the universe? You can tell them. Secrets of the universe hidden in every atom of our bodies. Hope you have a new understanding of atoms and a deeper understanding of the mysteries of the universe. Don't forget to like and follow the comments. Good night.